Hey PChemers, this is DW and this is the radiation lab. So we're going to be looking at different sources of radiation and different ways to deal with radiation. So let me give you the main point. There's three different types of radioactive particles or beams that we're going to deal with. There's alpha radiation, beta radiation, and gamma radiation. And then there's also different ways to deal with radiation. And so the main point of this exercise in this lab is to measure the differences and the ways to protect yourself from radioactivity using time, distance, and shielding. Just like in chemical substances that may be toxic to the body, the toxin is the dose. Well, the same thing goes for radiation in a sense that the dose of radiation is what causes the harm. So a small dose of radiation, like background radiation, your body can deal with the damage that those radioactive particles cause. But if you have a more intense source of radiation, then it causes damage to the tissues and your body has to process those damaged tissues. And so radiation sickness is really nothing more than your body processing dead tissues. So even if you get like a heavy sunburn, that's the same kind of thing. That's radiation sickness. If you're running a fever, it's because your body's repairing the damaged skin cells and so on from a severe sunburn. Well, we have different radioactive substances here. This is Depression era glass, when they thought it was in vogue to put uranium in the glass. And so this is a very mild amount of uranium glass. And we have a Geiger-Muller tube, a Geiger counter here. And so here we can see the background radiation is roughly between 7 and 13 counts per minute. So that's just from the concrete and the materials in the room, even our bodies. We have radioactivity and radioactive decay, and there's a little high voltage gas tube in here that will cause a breakdown if a radioactive particle goes in through this screen. And so a gamma ray or a beta particle or an alpha particle goes through this thin plastic window and ionizes the argon inside this tube, and we get a little voltage spike, and that's routed to a little speaker and we can hear it click. And so we can count those voltage spikes and we can know how many particles of radiation are entering the Geiger-Muller tube. And so we've been having this going for a while now. So the background, again, it's roughly between 7 and 13 counts per minute. And so if we have this uranium glass, we can put that over the Geiger-Muller tube and you can see that the count goes up a little bit. It's not very radioactive. It's just got a slight amount of uranium. And uranium has quite a long half-life, and so the radioactivity is not a very hot substance. So the longer the half-life, the less radioactive it is. This has got a little bit more uranium in it. You can see a darker green color to it. And it's going to give us a little bit more counts per minute. But we'd have to sit here and wait and count for a whole minute or two before we could detect the difference between these two. Even though optically we can see there's more uranium in this one. There's been, in the past, again, this was Depression era glass where they put uranium in the glass to give it that color. Fiesta ware, this particular orange glaze on Fiesta ware is uranium oxide. And so it has quite a bit of uranium in it. And you can tell the difference here by putting it up to the tube. And so we can count here for several minutes and we can get the radioactivity, the activity of this uranium oxide glaze on this Fiesta ware. Okay. Now, one thing that few people know, and that is that smoke detectors in the home have a radioactive source in them. And so this is the speaker over here on this side. This is the detector. Actually, it's the source of radioactive particles that goes onto a metal collector. And so this radioactive source is sending a constant beam of radioactive particles to the collector. And if smoke gets in the way, then that signal drops off and the smoke detector has detected smoke in that case. And so this is a nice detector because it's always on. So even if the power goes out, this signal can be detected and it can detect smoke. Now we have 9-volt battery typically applied here, and that's for the electronics to sound the alarm. But you could detect smoke without any power if you could measure the voltage that's generated on that collector from this radioactive source. Now you need a pretty bright source, and so this is pretty radioactive. Let's listen to it. And so that's the radioactivity that's present in a normal smoke detector, and that's americium, let's see, americium, what does it say here? 240, yeah. And so we can look that up, and so that's the radioactivity of the smoke detector. And you see it's thousands of counts per minute. Now, are all of these radioactive sources the same? The answer is no. Some are beta emitters, some are alpha emitters, and some are gamma emitters. And these are some gamma sources that I have. And so this is a little set of gamma sources that you can buy for calibrating various detectors, and also for playing essentially radioactive hide and seek. If you're training somebody to do decontamination, you can put these small sources underneath like a paper covering, and they can sweep around with their pancake detectors, and you can certify whether they're doing the sweep correctly if they found all the sources. And some of them are quite dim, they don't emit very much radioactivity or radioactive signal, and others are quite strong. Here's a cobalt 60, and cobalt 60 has a half-life of about 5.27 years, and so it's pretty active. So we can put that there. Now notice that's the gamma signal, and this tube is not very sensitive to gamma rays. So it's much more sensitive to beta particles. In fact, it's calibrated for beta particles. It's very sensitive to alpha particles, but for gammas, most of those gammas are going through our tube without causing ionization. But still, it's a strong enough source that we can detect it. This is a cesium-137 source. Its half-life is 30.07 years. It was manufactured in February of 2008, so it's pretty old, but still it has such a long half-life that it's going to still be quite strong. And so that's the cesium-137, and that's a gamma source, and so it's quite radioactive. Now none of these are dangerous outside of the body. These are all low enough sources. Even though we can really detect them strongly with our detector, they're not enough to cause dramatic damage or harm to me being here in their presence. They would be quite dangerous if I were to ingest them, especially the smoke detector. If I were to eat that source in some way, then those alpha particles would be emitted into my stomach and my gastrointestinal tract, where those alpha particles would do about 20 times the damage that they would do outside the body. And so they would be dramatically bad to ingest any of these sources. We're covered in a dead skin layer. Our whole bodies are protected by our dead skin cells, and so those dead skin cells are enough to stop most of these radioactive sources. So let's test that. We've talked about the different kinds of alpha particles. Let's test the ways to protect ourselves from radioactive particles. So I'm just going to mount this detector on a little rail, and for your lab you would use these little markings on here, and you would adjust the distance of the detector. So you'll have some data that was collected with the source in position. And so let's take a source and put it in position here at the end of the detector. And so we can set that to 0 inches. And we can count for a while, and this is the data that you will have available on the Blackboard site. And then we can increase the distance. So if I go an inch away, it'll drop a little bit. If I go another inch away, it'll drop a little bit more. And so one of the activities in the lab is to see, does it drop linearly with distance? Does it drop exponentially with distance? And so you need to look at the data and come up with a model that fits the data points that were collected at the different distances for the different sources. So this is the Fiestaware plate. It's going to have a certain profile with distance, and then the other radioactive sources will have a different profile. So let's look at the distance profile for the smoke detector. So you notice with the Fiesta wear plate, there really wasn't that much difference between 0 inches, 1 inch, 2 inch. So let's mount the smoke detector. Get it adjusted just right. Okay, so that's quite a large signal. In fact, it's so high, it's measuring right 30,000, 27,000 counts per minute. That's really high. In fact, the linearity of the detector kind of falls off because it's so high. But look, I only went half an inch, and now it's down to 145, 176. That's crazy. I mean, it was at 30,000 at 0 distance, and now I'm half an inch away, and it's down to 191. So what's going on here? Well, this is the characteristics we see from an alpha emitter. So think about the alpha particle. It's a helium nucleus. It's doubly charged. It's going to come out of that source, and it's going to find air. And what is air? It's nitrogen and oxygen primarily. And they have a lot of electrons. And so that alpha particle is going to rip electrons off of nitrogen, off of oxygen. It's going to collide with them, and it's going to be directed elsewhere and not into our detector. So it's going to be shielded by air. Another way to shield things, so that's distance. You can see the dramatic difference. Alpha particles are very easy to stop. So this is paper. This is just one sheet of paper in between the detector and the alpha particle. And so air can stop alpha particles. Paper can stop alpha particles, and so can your dead skin cells. But if you were to ingest an alpha emitter, that would be very bad because you don't have dead skin cells inside your body, and those alpha particles would cause extensive damage. Let's look at our Fiesta wear plate. So here we have our Fiesta wear plate. It's counting around 1,000 to 1,200 counts per minute. One sheet of paper. A little too close. Really no discernible difference. What if we quadruple it? So 4 sheets of paper. Really no difference. So if you wanted to tell the difference between an alpha emitter and a beta emitter, paper is your best probe. Because that's telling us that this Fiesta wear is not a beta emitter. Those beta particles are going right through the paper and into the detector, whereas the alpha particles were stopped by the paper. And so one of the things that you'll do for the lab is you have paper and you have copper. So here's some copper foil. There's 4 sheets of copper foil. Let's just try one. Not much difference. So those beta particles are going through the copper. Let's try 4 sheets of copper. This is metal shielding. Okay, it did decrease with copper. So we have 4 sheets of copper, and now we're starting to see a decrease in the beta particle emissions. This is actual tin foil. We call aluminum foil tin foil, but that's not true. This is real tin, and there's 4 sheets of tin here. If you look at the periodic table, tin is a lot heavier than aluminum and also a lot heavier than copper. And the signal dropped even more than the copper. So you can have this data in Excel. You can look at the different shielding values. And I want you to determine whether it's linear or exponential based upon the number of sheets of foil or aluminum, tin foil or aluminum foil or paper. So you have the data for all of those. You have it for the Fiesta wear plate. You have it for the smoke detector. I'm glad we have these other radioactive sources now. This is fairly new. I obtained them just like a year ago or so. And this cesium-137 is a gamma emitter. And so now we have the ability to test the alpha, the beta, and now the gamma emitter. So we'll put this in here. I am being careful not to aim the the source at my hands. This is the window of the source. It's a very thin plastic coating, so I don't have access to the actual radioactive material, but it's a thin enough plastic coating that the radioactivity is coming out. The backside is shielded, so it's safe to be on this side. It's fairly safe on the other side. It's just a pretty hot source, and so you'd want to protect yourself by not aiming it at your skin. Okay, I want to leave some room for our shielding. Okay, so there's our source. It's coming in right now about 8,000 counts per minute. So that's less than the alpha emitter for the smoke detector. That was 30,000 counts per minute. Let's try the paper. So this is gamma rays, 4 sheets of paper. Really no effect. I mean, it kind of went to 5,000. Here's the copper foil. Let's do aluminum foil first. So here's aluminum foil. Still around 5,000. Back up to 7,000 without it. Here's the copper. Okay, dramatic drop. Okay. So the gammas were able to go through paper, they were able to go through aluminum foil. When we got to copper, they dropped off dramatically. And then here's the tin foil. And it drops off dramatically as well. So that's the effect of shielding. And so if you want to shield yourself from beta particles and from gamma rays, the heavier the metal, that's the better shielding. So that's why in your dentist office and so on, they'll put lead aprons on you. So that's a heavy metal. It's cheap because lead is very abundant in the Earth's crust. And so it's just a very cheap, heavy nucleus metal. And that makes a very good shielding material. So the 3 main points for protecting yourself from radioactivity are time, distance, and shielding. What's the time factor? Well, you could sit here and set this on total counts and a stopwatch, and that's some of the data that you have as well. So you start the stopwatch and you count for 1 minute, 2 minutes is twice the dose, 3 minutes is 3 times the dose, 4 minutes is 4 times the dose. And so the longer you're in the presence of radioactivity, the higher your dose. And it's just linear with time, but you can show that in your spreadsheet analysis. And so those are the main points for our radiation lab. You have the data on Blackboard, and I look forward to your questions in the discussion group. Thanks.